In the vast, silent expanse of space where stars burn eternal and galaxies swirl in cosmic dance, a hidden danger looms: asteroids, the rocky relics of our solar system's birth. Imagine a massive space rock hurtling through the void at unimaginable speeds on a collision course with Earth. What would happen if such an asteroid struck our planet? How would we detect it? And, most critically, could we stop it? These questions drive the field of planetary defense, a scientific endeavor blending cutting-edge technology, international cooperation, and human ingenuity to safeguard life on Earth. This is the story of our efforts to understand and counter the cosmic threat of asteroids, a tale of vigilance, innovation, and the unrelenting quest to protect our fragile blue world from the perils of the cosmos. Asteroids are the ancient remnants of our solar system's formation, born 4.6 billion years ago in the chaotic crucible that forged the planets. These rocky bodies, ranging from mere meters to hundreds of kilometers in diameter, orbit the Sun in vast numbers, primarily within the asteroid belt between Mars and Jupiter. Their total mass, however, is a mere fraction of our moon's, a testament to their fragmented nature. Despite their diminutive size compared to planets, asteroids pose a significant threat when their orbits intersect Earth's. Each day, our planet plows through 200 to 300 tons of cosmic debris, tiny meteors and dust particles, including the fleeting streaks of shooting stars that grace our night skies. As Earth hurtles through its orbit at 18 miles per second, it sweeps up this material, a cosmic cleanup crew in perpetual motion. Yet, the total mass of these objects pales in comparison to Earth's, underscoring the rarity and catastrophic potential of larger impacts. To date, NASA has cataloged over 1 million asteroids, with approximately 26,000 classified as near-Earth objects, NEOs, those whose orbits bring them perilously close to our planet. Of these, over 2,000 are deemed potentially hazardous asteroids, PHAs, with 158 exceeding 1 kilometer in diameter, 2.5 times the height of the Empire State Building. These behemoths, though rare, could unleash devastation on a global scale if they struck Earth. The stakes are high. A single large asteroid impact could alter the course of life, as it did 66 million years ago, when a 10-kilometer-wide rock slammed into the Yucatan Peninsula, forming the Chicxulub crater and triggering the extinction of the dinosaurs. While no immediate threat looms, the specter of such an event compels scientists to remain vigilant, knowing that the history of life on Earth hinges on our ability to anticipate and avert such cosmic calamities. The Moon's pockmarked surface stands as a stark reminder of the solar system's violent past, its craters bearing mute testimony to countless asteroid impacts. Earth, too, bears scars from its cosmic encounters, though geological processes like erosion and plate tectonics have erased many. The Lunar and Planetary Laboratory at the University of Arizona estimates that Earth has endured up to 3 million impact craters larger than 1 kilometer, with the largest, such as the Vredefort crater in South Africa, stretching over 300 kilometers across. One of the most infamous events occurred in June 1908, when a 50-meter asteroid exploded over Tunguska, Siberia, releasing energy equivalent to 12 megatons of TNT. The blast flattened 80 million trees across 830 square miles, marking the largest impact event in recorded history. Far larger impacts in prehistory, like the Chicxulub event, a 100 million megaton cataclysm, reshaped the planet, wiping out 75% of species and paving the way for mammals, including humans, to rise. These events underscore a sobering truth: without a robust space program, humanity risks sharing the dinosaurs' fate. Preventing an asteroid catastrophe begins with detection, knowing where these celestial threats are and predicting their paths. Unlike the dinosaurs, whose rudimentary space program failed to avert disaster, humanity has developed sophisticated tools to monitor the skies. Governments and space agencies worldwide recognize asteroid impacts as a global concern, akin to climate change or pandemics, yet often overshadowed by more immediate threats. NASA, the European Space Agency, ESA, and others lead the charge, but amateur astronomers play a vital role, contributing significantly to the discovery and tracking of near-Earth objects. These dedicated enthusiasts, armed with telescopes and passion, complement professional efforts, scanning the heavens for objects as elusive as charcoal briquettes in the dark. Their contributions highlight the collaborative spirit of planetary defense, where every pair of eyes on the sky brings us closer to safety. Despite these efforts, our ability to detect asteroids remains limited. Current technology has identified only about 1% of the estimated population of near-Earth objects, capable of causing significant harm. Of the roughly 25,000 NEOs larger than 140 meters, small enough to evade easy detection but large enough to devastate regions, only 40% have been found as of November 2021. A sobering simulation conducted by NASA and other agencies underscored this vulnerability. Given a 6-month warning of an impending impact, none of Earth's existing technologies could stop a hypothetical asteroid. This exercise highlighted the critical need for early detection, ideally years or decades in advance to allow time for deflection strategies. To close this gap, scientists advocate for enhanced observatories such as the upcoming Vera C. Rubin Observatory, and space-based telescopes like NASA's NEO Surveyor, designed to spot threats long before they reach Earth. Detecting an asteroid is only the first step. Understanding its nature is equally crucial. Before deploying deflection strategies, scientists must characterize the asteroid, its size, composition, structure, and trajectory. Is it a solid monolithic rock, a loose rubble pile, or a metallic body? Each type responds differently to deflection attempts, necessitating tailored approaches. For instance, a porous asteroid might absorb an impact, while a dense one could be more easily nudged. This characterization relies on data from telescopes, radar imaging, and spacecraft missions like NASA's OSIRIS-REx, which studied asteroid Bennu up close. Such missions reveal not only the threat asteroids pose but also their scientific and economic potential, from unlocking secrets of the solar system's origins to offering resources like metals and water for future space exploration. Should an asteroid be found on a collision course, humanity has several strategies in its planetary defense arsenal. The most mature and feasible is the kinetic impactor technique, where a spacecraft slams into an asteroid at high speed, several kilometers per second, to alter its trajectory. Other proposed methods include the gravitational tractor, which uses a spacecraft's mass to slowly tug an asteroid off course via gravitational attraction, and nuclear deflection, which employs a controlled explosion to nudge or fragment the object. More speculative ideas include laser ablation, where lasers vaporize surface material to create thrust, or painting an asteroid white to alter its reflectivity, leveraging solar radiation pressure to shift its path. Each method requires precise knowledge of the asteroid and years of preparation, underscoring the importance of early detection. NASA's Double Asteroid Redirection Test, DART, launched in November 2021 aboard a SpaceX Falcon 9 rocket from Vandenberg Air Force Base, represents humanity's first full-scale test of asteroid deflection technology. Targeting the Didymos asteroid system, a binary pair comprising the larger Didymos and its smaller moonlet, Dimorphos, DART aims to demonstrate the kinetic impactor technique. Importantly, Didymos poses no threat to Earth, making it an ideal testing ground. In September 2022, the DART spacecraft smashed into Dimorphos at 6.6 kilometers per second, aiming to slightly alter its orbit around Didymos. Currently, Dimorphos completes an orbit every 11 hours and 55 minutes. Post-impact, scientists estimate this period could decrease by about 10 minutes, a subtle but measurable change. This mission is a proof of concept, showing that a well-timed impact could deflect a threatening asteroid if detected early enough, potentially averting disaster. Beyond their threat, asteroids captivate scientists for their scientific and exploratory value. These celestial wanderers are time capsules, preserving clues to the solar system's formation. Missions like Japan's Hayabusa 2 and NASA's OSIRIS-REx have returned samples from asteroids Ryugu and Bennu, revealing insights into the building blocks of planets and the origins of water and organic molecules on Earth. Moreover, asteroids hold potential as resources for future space exploration, with metals like iron and nickel, and water for fuel or life support. From a planetary defense perspective, understanding asteroids' composition enhances our ability to predict and mitigate impacts, turning these cosmic threats into opportunities for discovery and innovation. The specter of an asteroid impact is a global challenge, demanding international cooperation and sustained investment. While no known asteroid larger than 140 meters poses a significant threat for the next century, the incomplete catalog of NEOs reminds us of the work ahead. Initiatives like the United Nations-endorsed International Asteroid Warning Network, IAN, and the Space Mission Planning Advisory Group, SMPAG, foster collaboration, ensuring that nations share data and coordinate responses. Future technologies, from advanced telescopes to next-generation deflection systems, will bolster our defenses. Yet the true power lies in humanity's collective resolve, to watch the skies, to understand the cosmos, and to act decisively to protect our shared home. The story of planetary defense is more than a tale of science and technology. It is a reflection of humanity's determination to endure. The dinosaurs, mighty as they were, succumbed to a cosmic bolt from the heavens. We, their successors, wield the tools of reason and innovation to avert a similar fate. As we gaze at the stars, we are reminded of our fragility and our strength, a species capable of peering into the depths of space, anticipating dangers, and forging solutions. Asteroids, both threat and treasure, connect us to the universe's ancient past and its boundless future, urging us to remain vigilant stewards of our pale blue dot. Thanks for watching. If this exploration of asteroids and humanity's quest to defend Earth has inspired you, show your support by subscribing, ringing the bell, and enabling notifications to never miss videos like this.